Hi everyone. In this video I'm going to present a 3x3 matrix. I'm going to calculate its eigenvalues, its eigenvectors, then I'm going to determine if it's diagonalizable, and if so, to determine the invertible matrix that allows it to be done. And finally I'm going to determine the exponential of this given matrix. So if you want to be stronger than you were at the start of the video, pause and try and make progress towards the answers on your own. With that said, let's get started. So this is the matrix here. A equals 1, 3, 3, negative 3, negative 5, negative 3, 3, 3, 1. So we're interested in solving the eigenvalue problem AX equals lambda x. So we're interested in solving for the scalar eigenvalues lambda, as well as the eigenvectors x. So I'm going to bring lambda x to the left side. I'm going to factor x. Now, in order to avoid the trivial solution, this matrix in parentheses here, A minus lambda I, must not be invertible. That is, its determinant must be 0. So, to find the eigenvalues, I take the given matrix and I subtract lambda from each of the elements along the main diagonal. 1 minus lambda, 3, 3, negative 3, negative 5 minus lambda, negative 3, and then 3, 3, 1 minus lambda. And this is equal to 0. Alright, so this is a 3x3 matrix, so I'm going to use expansion by minors to evaluate the determinant. So the first term is 1 minus lambda. The minor is negative 5 minus lambda, negative 3, 3, 1 minus lambda, and now minus 3. I'm going across from left to right here, so minus 3. And then the minor is negative 3, 3, 1 minus lambda. And finally, plus 3, negative 3, negative 5 minus lambda, 3, 3. This is equal to 0. Alright, so I'm going to evaluate each of these 2x2 determinants. 1 minus lambda, negative 5 minus lambda, 1 minus lambda, and then subtract the product, so it's going to be plus 9. And now minus 3. This is going to be negative 3, 1 minus lambda, plus 9, and plus 3. Negative 9 plus 3 times 5 plus lambda equals 0. Okay, so now I'm going to expand further. This is 1 minus lambda. So in here I have negative 5 plus 5 lambda minus lambda plus lambda squared plus 9 minus 3. This is negative 3 plus 3 lambda plus 9 plus 3, negative 9 plus 15 plus 3 lambda equals 0. One minus lambda. Now if I combine like terms here, I get lambda squared. This is plus 4 lambda and plus 4 and minus 3. That is 6 plus 3 lambda plus 3 lambda. That is 6. Let's see, this is minus 18 minus 9 lambda plus 9 lambda plus 18. So these cancel. And what we're left with then is 1 minus lambda. Lambda squared plus 4 lambda plus 4. That factors to lambda plus 2 squared equals 0. So the eigenvalues are -2 and 1. The eigenvalue -2 has a multiplicity of 2, and the eigenvalue 1 has a multiplicity of 1. So now that we have the eigenvalues, we have to plug them into this vector equation right here. We're going to do each one in turn. I'm going to start with I'm going to call the first eigenvalue lambda 1, 1. So I have a minus lambda I, lambda 1, x1 equals 0. So I'm plugging in this first eigenvalue here into the equation, and I'm going to solve for x1. So I'm going to subtract each of the elements along the main diagonal by 1. So the first element here is going to be 0, 3, 3. Let's see, -3, -5. Oh, I'm sorry. That's -6, -3, and now 3, 3, 0. And for the eigenvector itself, I'm just going to use the generic elements x1, x2, x3 equals 0, 0, 0. So now I multiply these matrices on the left. The first equation, I get 3x2 plus 3x3 equals 0. Second equation, I get -3x1 minus 6x2 minus 3x3 equals 0. And 3x1 plus 3x2 equals 0. So based on the first equation, if I solve it for x3, I get -x2. And if I solve the third equation for x1, I get -x2. So the eigenvector associated with lambda equals 1 is x1 equals x1, x2, x3. This is -x2, x2, -x2. And x2 is an arbitrary constant, so I can pull it out in front of the matrix, or of this column vector, I should say. And this is x2 equals -1, 1, -1. So this here is my eigenvector. Now you might ask, why is there an arbitrary constant here? Well, if we go back to the very first equation here, x appears on both sides. So let's say if I were to multiply both sides by 3, the 3 would pair with the x. So basically, both sides can be multiplied by any constant, and that's why there's an arbitrary constant here, because the equation is homogeneous in the eigenvector. All right, so let's move on to the next eigenvalue here, lambda equals -2. Lambda 2 equals -2. A minus lambda 2I x2 equals 0. Okay. So if I subtract lambda 2 from each of the elements along the main diagonal, that means I have to add 2. So this will be 3, 3, 3, -3, -3, -3, and 3, 3, 3. And for the eigenvector x2, I just use the generic elements x1, x2, x3. And the 0 column vector is 0, 0, 0. So if I multiply these two matrices on the left here, I get the same equation. I just get 3x1 plus 3x2 plus 3x3 equals 0 for the one on the top. If I solve this for x1, I get -x2 minus x3. So the eigenvector x2 is x1, x2, x3. This is -x2 minus x3, x2, x3. This is, if I split it up into one vector that's in terms of x2 and another that's in terms of x3, I get -x2, x2, 0 plus -x3, 0, x3. And this is x2, and if I bring the arbitrary constants in front, I get x2 -1, 1, 0 plus x3 -1, 0, 1. So there are two eigenvectors associated with lambda equals -2. So in total, there are 3 eigenvectors associated with these two eigenvalues, and since this is a 3 by 3 matrix, and there are 3 eigenvectors, this is in fact diagonalizable. That means that D is equal to P inverse AP, where D is the matrix with the eigenvalues along the diagonal. So what are they? -2, -2, and 1, with zeros everywhere else. Now the reason we write -2 twice is because there are two eigenvectors associated with it. So the matrix P is the invertible matrix that allows us to diagonalize it. It's constructed by using the eigenvectors that we found. So for -2, I have to place the eigenvectors for -2 in these two columns, the first two columns for P. So I'm going to put -1, 1, 0 first. And I'm going to put -1, 0, 1. -1, 0, 1 for the second column. And for the eigenvector corresponding to lambda equals 1, I'm going to use -1, 1, -1. -1, 1, -1. All right, so now we can check that that if I multiply this out, I get the eigenvalues along the main diagonal. Oh yeah, so if I plug in the matrix A and find out what its eigenvalues are, I do get -2, -2, and 1. The eigenvectors, -1, 0, 1. -1, 0, 1, that's this column right here. -1, 1, 0, that's this column right here. And 1, -1, 1. So it's okay that it's off by a constant factor. I can, because x2, x3, and x2 are arbitrary, I can multiply by whatever I want. So it's okay that it's off by a constant factor. So I'm just going to plug in this matrix here. So -1, -1, -1, and 1, 0, 1, and 0, 1, -1. And this here is the matrix A, so this should give me D. And indeed, I get the matrix -2. In the first row, I have -2, 0, 0. In the second row, 0, -2, 0, and the third row, 0, 0, 1, as predicted. So this is so P is in fact the invertible matrix that diagonalizes A. So finally, I want to find the exponential of A. Now, the exponential of A is defined by the Taylor series centered at 0. This is 1 over n factorial a to the power of n. Now, to get a to the power of n, I'm going to solve this equation here for a. So I'm going to pre-multiply both sides by p. PD equals p inverse AP. This here is the identity matrix. So PD equals AP. And finally, to solve for A, I'm going to post-multiply both sides by P inverse. PD P inverse equals AP P inverse. This here is the identity matrix also. So I have A equals PD P inverse. And this means that, so for example, if I wanted to find out what a squared is, that would be PDP inverse times P dP inverse. Matrix multiplication is associative, so I can multiply P inverse and P. That's the identity matrix, and this will give me P d d P inverse, which is P d squared P inverse, and it's the same for higher powers of A. So in general, a to the power of k is P times d to the k P inverse. Now the nice thing about d is that it's non-zero only along the main diagonal. So d to the k is actually negative 2 to the k, negative 2 to the k, and 1 to the k, which is just 1. So, and everywhere else it's 0. And times P inverse. So I'm going to plug in. So it is kind of tedious to evaluate this this triple product. I mean this product of three matrices. So I'm going to use the computer for that. So so this here is going to be P and d to the power of k, that's this one, negative 2 to the k, 0, 0, 0, negative 2 to the k, 0, 0, 0, 1, okay? And times the inverse of p. All right, so this is the results. I'll write it in matrix form so that it's easier to see. All right, so this is equal to n equals 0 to infinity, 1 over n factorial, and now a to the n. So this is going to be one on the top left, and then 1 plus negative 2 to the k minus 2, or oh, I'm sorry, this is to the n. One plus negative 2 to the n minus 2, so then times negative 2 to the n. Okay, and now the top right, this is going to be 1 minus negative 2 to the n. And middle left is going to be negative 1 plus negative 2 to the n. And then in the center is going to be negative 1 plus 2 plus 2, negative 2 to the n. And center right is going to be negative 1 plus negative 2 to the n. And now bottom left is going to be 1 minus negative 2 to the n. Same thing for the bottom middle, and then 1. Okay, so now I'm going to distribute this into each of the elements here. So this is equal to so for the top left, I just have sum n equals 0 to infinity 1 to the power of n over n factorial. In the top middle, I have n equals 0 to infinity 1 to the power of n over n factorial plus negative 2 to the power of n over n factorial minus 2 negative 2 to the n over n factorial, and in the top right I have 1 to the n over n factorial minus sum n equals 0 to infinity negative 2 to the n over n factorial. All right, center left. N equals 0 to infinity. Oh, this is negative. And then 1 to the n over n factorial plus sum n equals 0 to infinity negative 2 to the n over n factorial. Center middle, this is going to be negative 1 to the power of n over n factorial plus 2 negative 2 to the n over n factorial one to the n over n factorial, and then plus negative 2 to the n over n factorial. Bottom right is just 1 to the power of n over n factorial, and then bottom left and bottom middle. Minus. All right, finally. So e to the a is equal to. So the top left is just going to be e to the 1, which is, I'll just leave it as e to the 1. And now e to the 1, and now for the top middle, this is going to be e to the 1 plus e to the negative 2 minus 2 e to the negative 2 so then that's just minus e to the negative 2. I'll just leave it like that for now. So top right is going to be e to the 1 minus e to the negative 2. Center left, this is going to be negative e to the 1 plus e to the negative 2. And now in the center, I have negative e to the 1 plus 2 e to the negative 2. Center right, I have negative e to the 1 plus e to the negative 2. Bottom right, I have e to the 1. Bottom middle, I have e to the 1 minus e to the negative 2. Bottom left, I have e to the 1 minus e to the negative 2. All right. So let's evaluate this the matrix exponential of the matrix in C. All right, so in the top left, top left and bottom right are good. It's E, and in the top center I have E and then minus e to the negative 2, yep. In the top right I have e minus e to the negative 2, that's good. Center left I have negative e plus e to the negative 2, that's good. In the center I have negative e plus 2e to the negative 2, that's good. In the center right I have negative e plus e to the negative 2, that's good. In the bottom left I have e minus e to the negative 2, that's good. And then in the bottom middle I have e minus e to the negative 2. So we did that correctly, thank goodness. Alright, so that's it for this video. Thank you all for watching.